Well, hello. We're looking at enzymes today, and the enzyme we're looking at is catalase. And I could have used anything as my source of catalase because it's in just about every cell. I mean, I could have used potatoes, I've got them here. I could have used liver, but I've instead chosen yeast. And the reason I've chosen yeast is I can keep the cells nicely alive by adding some sugar, and you can see the sugar over there. And these have been soaking quite nicely in the sugar for quite a long time. They started off about 35 degrees Celsius and they're now like 27.4 degrees Celsius. So they should be quite happy now. They've had a bit of a feed of glucose, and because they've had a bit of a feed of glucose, they should have come to life in the hour and a half that I've left them there. So they should be nicely ready to work. And these yeasts contain peroxisomes. Peroxisomes are like lysosomes, but they're a little bit specialized. They contain enzymes like peroxidase, or the most common one that we talk about, catalase. And catalase is the fastest enzyme. Literally, millions of molecules of substrate per second go through each catalase molecule. The substrate that it breaks down is H2O2. It's hydrogen peroxide. And you're probably used to this sort of thing sold in drugstores because it's quite good for antiseptic. In other words, it kills cells. And therefore, because it kills cells, you don't want it in your cells. So your cells try to break it down. The equation of the reaction that the enzymes catalyze is 2H2O arrow, so equals, start again, 2H2O2, because this is hydrogen peroxide, arrow 2H2O plus O2. So you can see the products of this enzyme catalyzed reaction are pretty innocuous, oxygen and water, which is a pretty good return from something as nastily poisonous as this. And it is nastily poisonous. When I first did this experiment, I was in Turkey and they sell it as something like 33% hydrogen peroxide. So I was there happily doing it without gloves, and after a little while, my hands started to tingle. I noticed they were turning white. So I washed my hands and the tingling went away, but then it quickly came back, and my skin went white and flaked, and it was fairly awful. Hence the gloves, even though I've only got 3% here. So let's have a look what we've got here. Firstly, I'm going to look at the effect of temperature on the rate of the enzyme-controlled reaction. So the first one I'll look at is this test tube. It has 23.6 degrees Celsius. Now, it doesn't have to be 37, 38 degrees for the optimum temperature. That tends to be the optimum temperature of enzymes in the human body. And yeasts, of course, don't tend to operate at such high temperatures as mammals like us. So, what I intend to do is this. This one is at its, I'll just check that that's the right one. Good, so that's 23 point something or other now. I'm not waiting for it to happen. And what I'm going to do is stick some of this in, which is the hydrogen peroxide. Here's the yeast, which has got the catalase enzyme. Put this in, try and remember where it first was, and then have a look at the highest level of foam. And you can see if it forms water and oxygen, there, it's going down now. If it forms water and oxygen, it's going to form bubbles. It makes complete sense. Oh, it went up a bit. But it's still going up. Sometimes it reaches up to there. Okay, so let's come to the top of the tube now. Well, this is awesome. That's going very, very well. And I suggest it's going to come from, well, I can see a layer of oxygen from there to there. In fact, I think I'll do it from there to the top because that's where it reached. And that ends up being 85 millimeters. It is going down now. Now my next little thing here has been in the freezer. And it's been out for a little while I've been preparing the video, and now it is 14, 12.5, 12.3. I didn't obviously get it down to 0 because it didn't actually freeze, and it's now 12.7, 12.8. So now I'm going to take the same amount of hydrogen peroxide that I had before, plunge it in, and it's not doing much at all. It's doing a bit. There's about 5 millimeters, getting a bit higher. About 10 millimeters. It's working though. So this one at 12, 13 degrees Celsius, I think it's starting to go down now. It got to about 12 millimeters. Now let's have a look at this one that's bubbling away on here. It's been on the hot plate. I've been heating up the stuff inside it. And let's have a look at this one. 61, 82, 86, 87, 88.4. And it should top out at about 90 degrees. No, it's 88.3 or thereabouts. So let's see what this one does when I stick some hydrogen peroxide in. That's the same as before. Absolutely nothing. So, at a high temperature, 88 degrees, it did nothing. At a medium temperature, around about 24 degrees, it produced around about 85 millimeters of bubble. At something like 14 degrees, 12 degrees, I've forgotten what it was. Let's measure that. That's a bit of a sleeper. It did 60 millimeters. So, there we've got a bit of a puzzle that you have to explain. Why is it that it works well at a sort of medium temperature? Why does it work less well or less quickly at a lower rate, at a lower temperature? And why did it fail to work at all at 90 degrees or near to that? The answer comes in kinetic theory, in what particles do when you heat them up and when you cool them down, when you give them more kinetic energy, when you give them less kinetic energy, and we'll look at that in a while. It also looks at the nature of enzymes. Enzymes are proteins. Proteins have a three-dimensional shape held together by hydrogen bonds and ionic bonds and the rest of them. And so, the temperature obviously has an effect on the enzyme itself. The next thing we're going to do is, let's just bring this down for a minute, we're going to have a look at the same things that I did before with the pH scale. So I've just used serial dilution to make my range of pHs, and I've used a very quick cabbage indicator to show the pHs, and I've got the full range from 0 to 14. And when I come back to this, I will put those together and we'll look at the effect of pH on the rate of an enzyme-controlled reaction.